In this video, we'll be reviewing section 2.7 on optimization. The objectives of this video will be to define local and global extremes, which are maximums and minimums. We'll also review how to use the first and second derivatives test to identify where these extremes occur on a graph. Let's start with the definitions of our local extrema. F has a local maximum at a point A if f of A is greater than or equal to f of x for all x near A. Similarly, F will have a local minimum at A if f of A is less than f of x for all x near A. F has a local extreme at A if f of A is a local maximum or minimum. The process of finding the maxima or minima is called optimization. A point is a local max or min if it's higher or lower than all the nearby points. These points come from the shape of the graph. The idea here for a local maximum or minimum is that it's for the x values near a certain point A, not overall in the entire graph. That would be our global extrema. F has a global maximum if at A if f of A is greater than or equal to f of x for all x in the full domain of F. Similarly, for the global minimum, f of A has to be less than f of x for all x in the domain of F. And then F has a global extreme if it has a global maximum or a global minimum or both. A point is a global max if it's higher than every point on the graph, or similarly for minimum, if it's lower than every point on the graph. These points come from the shape of the graph and the window with which we view the graph. So oftentimes you'll find global extrema if you have a condensed or compressed domain. So what we have then is that local max or min of f will occur at what we call a critical point, and the way we identify a critical point is by using the first derivative. So a critical number for a function f is a value x equals a in the domain of f, where either f prime of a equals 0 or f prime of a is undefined. A critical point for a function f is a point a f of a, where a is a critical number of f. So the idea is that a critical number will occur wherever the first derivative either equals 0 or is undefined, and then local max and mins will only occur at those critical points. So we want to find all critical points of the function f of x equals x cubed minus 6x squared plus 5. So we'll find all the critical numbers. That is all of the x values that make the derivative of f equal to 0 or undefined, and then we'll plug those values back into the original function to get their critical points. What we want to take a look at here to decide is if the derivative will be undefined. What we have here is a cubic function, and we know that cubic functions are continuous over their entire domain. And so their derivative, which will be a quadratic, which we'll see in a second, will also be continuous over its entire domain. That's just the property of continuous functions. So let's take a look at the derivative of f using the power rule and the sum and difference rule of derivatives. So we'll have 3x squared minus 12x plus 0. And to find the critical numbers, we'll set the first derivative equal to 0 and solve. We can factor out 3x, and we're left with x minus 4 equals 0. By the zero product property, we have 3x equals 0 and x minus 4 equals 0, giving us the critical numbers of x equals 0 and x equals 4. To find the critical points, we'll be plugging these values back into the original function. So our first critical point will be when f is evaluated at 0, which is the point 0.05. The second will come from evaluating the function at 4. The second critical point will happen at 4, negative 27. Let's review how to identify if the critical point will result in a maximum, minimum, or in some cases, neither. Once we have found the critical points of f, we still have the problem of determining whether these points are maxima, minima, or neither. The critical numbers only give the possible locations of extreme. The key here is that they're possible locations, not necessarily are. And some critical numbers are not the locations of extremes. The critical numbers are the candidates for the locations of the maxima and minima. F prime and extreme values of f. There's 4 possible shapes of graphs are shown here. In each graph, the point marked by an arrow is a critical point where f prime of x equals 0. What happens to the derivative near the critical point? So we have this point identified in each graph. That's the critical number. And the first case it results in a maximum because to the left of the critical point or critical number, the first derivative is positive, and to the right, the first derivative is negative. Remember, first derivative relates to the slopes of the tangent lines to the curve. In the second case, the critical number results in a minimum. To the left of the critical number, the slopes of the tangents are negative, so the first derivative is negative on this interval. This is going to be the key for using our first derivative test. And then to the right of the critical point, the first derivative or the slopes of the tangent lines are positive on that interval. In the third and fourth case, it's not a minimum or a maximum. We can see that we go from positive slopes to positive slopes, but for some reason, this still gave us a critical number, and we'll see why. And alternatively, we go negative slopes, but we still ended up with a critical number here. So the first derivative test says to start by finding the critical points of f. For each critical number, examine the sign of f prime to the left and to the right of c. So you're going to use each critical point of f to break up a number line to create intervals to test around those critical numbers. You don't want to test the critical number because we know for a fact that if you plug the critical number into the first derivative, the output is going to be 0. What happens to the sign as you move from left to right? If f prime changes from positive to negative at x equals c, then f will have a local maximum. So we're going from positive first derivative to negative first derivative, and we'll have a maximum. Alternatively, if the first derivative goes from negative to positive, we'll have a minimum. If f prime doesn't change at all, it's neither a local max nor local min, and we'll need to do a little bit more research. So we'll use the first derivative test to determine whether f of x equals x cubed minus 6x squared plus 5 has any local extrema at the critical points found in the previous example. So just as a reminder from the previous example, we found the critical numbers of x equals 0 and x equals 4, and their associated critical points, which I'm going to signify as CP, was 0, 5, and 4, 27, 4, negative 27. So to use the first derivative test, we'll use our critical numbers to break up a number line into intervals, and we'll plug those into the first derivative. So we'll also need to identify that for our use. Our first derivative was 3x squared minus 12x. So we'll be plugging into that function. It may help us to have the factored form as well. So 3x times x minus 4. So we have 0 and then 4. In the interval from negative infinity to 0, we could plug in negative 1. In the interval from 0 to 4, we could plug in positive 1. And the interval from 4 to infinity, we could plug in positive 5. So I'm going to plug into 3x times x minus 4. I've got negative 3 times negative 5, which is positive 15. So the first derivative is positive on this interval. When I plug in positive 1, we're looking at 3 times negative 3, which is negative 9. So the derivative is negative over this interval. And when we plug in 5, the output is positive 15. And so the derivative is positive over this interval. So notice that we're going from positive slopes to negative slopes. And so a maximum will occur at 0. And then we're going from negative slopes to positive slopes. And then a minimum will occur at 4. So we have a local, this is all we can identify because we don't know about the rest of the graph. We have a local maximum at the critical point 0, 5, and a local minimum at the critical point 4, negative 27. In the next video, we'll review the second derivative test for extremes.